Hi, welcome to the lesson on tension. Tension is a force applied by a cable, and in a problem you can pretty much treat it just like any other force. Once we cover elasticity and Hooke's law, we'll see that as objects move, sometimes tension forces change, but here we're just going to look at static tension. And the great thing about tension forces is that they act through a cable or a string or any kind of long bit of matter. And you can tell which direction the force is acting by the position of the cable, and that's very, very useful. So let's look at a few little examples of where tension acts. Say we have a ball hanging by a string. You know what, I want this line to be straight. And the ball has a weight, M equals 5 kilograms. That ball, if the string were cut, would drop to the ground, because it also has a weight force acting on it here. And that weight force equals mg, or here, 50 newtons. So there has to be some kind of other force in the string, which is balancing out the weight force that when we cut the string is removed, and this would be the tension force. Since this ball is not moving, the sum of forces is equal to 0. That means the tension force has to exactly equal the force pulling down, which is 50 newtons. This is a very simple problem. If you have a ball of 5 kilograms hanging by a string and not moving, the tension force is 50 newtons. But of course, as with everything in this course, it gets more and more complicated. Say we had a particle suspended by 2 strings at an angle, and the particle had mass, say mass equals 10 kilograms. This particle has tension force, let this be tension force 2, this be tension force 1. Actually, I'll change those around. Actually, who cares? Tension force 1, tension force 2. And the weight force, 100 newtons. And the angles in here are 30 degrees and 30 degrees. And this ball is stationary. Therefore, acceleration equals 0. And we also know that since sum of forces equals ma, if A equals 0, then the sum of forces equals 0. Sum of forces equals 0. So these 3 forces, 1, 2, 3, all have to balance each other out. The first thing we do is change the tension forces, not into these annoying slanted forces, but into horizontal and vertical components. So we'll work horizontally, and vertically. Let's look at the horizontal component. We'll make it red. That can run along here. This horizontal component of this force is given by T2 cos 30 degrees. And this horizontal component here is given by T1 cos 30 degrees. Now the vertical component to these two forces, this is given by T2 sine 30 degrees, and this one by T1 sine 30 degrees. Now we've done this, we can pretty much ignore these forces here. Let's only think about them in terms of these square components, horizontal and vertical. So the first thing we need to say is that horizontally, the acceleration is 0. The particle is not moving to either side. Therefore, T1 cos 30 degrees, which is this horizontal force, must balance out with this horizontal force, because these are the only 2 horizontal forces working on this object. So that equals T2 cos 30. Divide both sides by cos 30, we have tension 1 equals tension 2. That's interesting. So both these tensions have to be the same. The tensile force T1 has to equal the tensile force T2. Now vertically, we have T1 sine 30, that's part of the upward force, plus, we need a longer line for this, T1 sine 30 plus T2 sine 30, the upward forces here and here, has to equal the downward force, 100 newtons. And we also know T1 equals T2, so we can sub that in here, replacing T2 with T1. So we have T1 sine 30 plus T1 sine 30 equals 100. Therefore we have 2 T1 sine 30 equals 100. T1 equals 100 over 2 sine 30 degrees. Sine 30 degrees equals a half, so this is 100 over 2 times a half, which is equal to 100 newtons. The tension force of T1 equals 100 newtons, that's here, and T2 also equals 100 newtons. So by taking the tensile force, breaking it up into its horizontal and vertical components, and then understanding that both the vertical components, here being 3, have to sum to 0, and the horizontal components have to sum to 0, we can work out exactly what that tension is. Now I've got an even more difficult problem in front of me here, which I'm going to try and get down. This one involves some really serious trigonometry. It's the kind of thing you'd see at the end of the forces section, maybe on a SAC. Particle T1 acting at 30 degrees to the horizontal. T2 acting at 60 degrees to the horizontal, and of course we know there is a weight force mg, and m equals 10 kilograms, so this equals 100 newtons. The particle is not moving, therefore the sum of forces has to be 0. Here's where it gets a little bit tricky. We'll talk about horizontal and vertical components of forces. So let's break up these tension forces. T1 has 2 components. First component is T1 cos 30 degrees. Vertical component is T1 sine 30 degrees. T2 has T2 cos 60 degrees and T2 sine 60 degrees. And of course the gravity force is also a vertical force. So we can pretty much ignore those original forces, and now we only think of the horizontal and vertical components. So first of all, the horizontal components have to sum to 0, so we'll work over here. We know that T2 cos 60 degrees equals T1 cos 30 degrees. You can't divide by the same cos value on both sides. You can't just cancel the coses. If only, imagine how easy maths would be if that were the case. So we have to leave that relationship for now. We cannot say T1 equals T2. In fact, T1 does definitely not equal T2. But we do know there is this relationship. And in fact, what I'm going to do is try and get T2 by itself. T2 is equal to, what do we have here? T2 equals T1 times cos 30 degrees over cos 60 degrees. That's dividing both sides by cos 60 degrees. Now, horizontally. Oops, sorry. Oh gosh, that was horizontally. We're going to do vertically. Here we go. T2 sine 60 degrees. That's this horizontal. That's this vertical force here. Plus T1 sine 30 degrees is equal to 100 newtons. If we sub in this value for T2, so we take this and put it over here, we can eliminate T2 from this equation. So we have T1 cos 30 degrees over cos 60 degrees multiplied by sine 60 degrees plus T1 sine 30 degrees equals 100. Take T1 out the front as a factor. T1 cos 30 degrees sine 60 degrees over cos 60 degrees plus sine 30 degrees equals 100. Divide both sides by this part here. T1 equals 100 over cos 30 degrees sine 60 degrees over cos 60 degrees plus sine 30 degrees equals 100. Okay, let's figure out what's going on here. Cos 30 degrees is root 3 on 2. Sine 60 degrees is also root 3 on 2. Cos 60 degrees is a half plus a half. That's 100 over 3 on 4 on 1 on 2 plus a half. That's equal to 100 over 3 on 2 plus 1 on 2. That's equal to 100 over 4 on 2 equals 50 newtons. So T1 equals 50 newtons. T1 equals 50 newtons, coming all the way from over there. And we know therefore that T2 equals T1 times cos 30 over cos 60. That's equal to 50 times cos 30 is root 3 on 2 over cos 60, that's a half. That equals 50 times root 3, and that is equal to 86.6 newtons. So with a bit of effort and a lot of trigonometry, we can find that since the resulting force is 0, everything has to balance out, and by dividing the problem up into horizontal and vertical components and then combining what we know, we can solve both T1 and T2. There will be a few example questions being done for this type of problem in other videos. If this was confusing, check those out, and I think you'll find it much easier to understand once you've seen it done a few times.